Well, hey everyone, we're going to take a look at question 18 through, well, I'm not sure when we're going to stop, but we're definitely going to start with question 18 on your AP Calculus B final exam. So, question 18 is use tabular integration to find the following antiderivative. So I'm just going to go ahead and put the normal chart that we always use if we're going to use tabular integration. Up over in the integrand, we can see an x squared minus 3x, which is an algebraic function. And then we also see an e to the x, which is exponential. So algebraic has priority here. So x squared minus 3x, that's going to be my u. And then from here, you should probably know what to do. The u side, we're going to take the derivative. In the dv column, we're going to take the integral. And then we're going to multiply those two together, 2x minus 3 multiplied by e to the x. And taking a look at what we have in this bottom right-hand box, that is not integratable, so we'll do the same thing again. The derivative of 2x minus 3, the antiderivative of e to the x, and then we'll multiply. So now we have something which is integratable. So 2e to the x, we can definitely get an antiderivative there. But I also note that 2, if I go the derivative one more time, I'm going to get a 0, which is much nicer to get to the 0. So we're going to take one more derivative and one more integral. Now that we've got our zeros in the bottom right and bottom left here, we're going to assemble our antiderivative by going diagonally from top left to the next row on the right. Then we'll subtract the next diagonal. And then add the next diagonal. And since we have reached the 0 row, we're just going to put a plus constant at the end, and that should do it for the antiderivative. Now the rest of this is just going to be simplifying. So we'll group everything except for the c, and we'll note that everything inside the parenthesis has an e to the x, which we can factor out. And the next we're just going to combine like terms in here. And then we combine like terms. Now somewhere along the way, I seem to have made an algebra mistake. I think I'm looking at the answer key right now. So let's rewind this before we started simplifying. And I think it was right here where I forgot to distribute that negative sign to the 2x. So here's what we should have had. And then now we'll just combine like terms real quick. And that should do it for this problem. Probably a little longer than I wanted to spend on it, but it's good to see that we still make algebra mistakes, even the best of us. So you should always be looking out for it. All right, let's get to the next one. Evaluate the integral using a substitution prior to integral by parts. Now this whole business about using a substitution before integral by parts, yeah, I don't think we're going to do that. We're just going to use integral by parts because there's really nothing unusual about this integrand. So looking at this, just like before, we have an algebraic x squared and an exponential e to the 4x. So our algebraic will be our u function, and our exponential will be the dv function. Now be a little careful with this one because the antiderivative here of e to the 4x, you're going to get a 1/4 e to the 4x every time you take an antiderivative there. So this was our first line, so of course we're going to have to take the derivative of x squared, the antiderivative of e to the 4x, and then multiply. which is not integratable, so we'll do the same process again. Derivative, integral, multiply. And this is actually integratable now, my u dv. 2e to the 4x over 16. Definitely you can take an antiderivative of that. However, looking at the u column, I see a 2. So I'd much rather get a 0. So I'm going to go ahead and take one more derivative. And then one more integral. And that's great, because now with that 0, I can start assembling my antiderivative. Cool. We're going to start with the first diagonal, which is an addition diagonal, always addition to start off with, followed by a subtraction, and then followed up with an addition. And since we have the 0 in the last row, we're just going to add a plus c at the end. Okay, that is all of the integration. The next step, which is often the most difficult part of this, is we're going to try to simplify this. So we're going to see what we can factor out. Let's start off by doing all the multiplication. Now, in this first set of multiplication, there's really nothing to multiply, so we'll just kind of move it all together. And in the second addend, we have ourselves the 2 and the 16th. So kind of mixed whether or not I want to simplify that. Yeah, we should simplify that. 2 over 16 is 1 over 8. And then we'll just move it all together. And then in the next addend, we're going to simplify the 2 over 64. 64 is 2 times 32. And now we can cancel. And we don't need the parentheses anymore. Great. Let's group everything except for the c. And we'll factor out those e to the 4x's. Now it looks like the least common multiple of the denominator is 32. So let's turn everything into 32. So 1/4, that's 8 over 32. And then 1/8, that's 4 out of 32. Then we're going to factor out 1/32 from everything. And that should just about do it for this problem. Number 20, we've got solving an initial value problem, and we're also going to have to use a integral by parts on this one because I'm looking at x cubed and e to the negative 2x. So let's find our antiderivative first. And looking at my integrand, I can see that I have, once again, a algebraic function, and we have also an exponential function. So the algebraic function is going to be my u, and my exponential function will be dv. Now I'm kind of being conscious of multiplying everything over at the end just to know when I should stop, although I have a feeling we'll be able to get to 0 on this integral by part also. Okay, let's take our derivative. Let's take our integral, and then we'll multiply. And that doesn't look integratable, so we'll do this process again with a derivative, an integral, and a multiplication. And we're getting there. This is not quite different or integratable yet, so we're going to do another derivative, another integral, and then multiply again. And this is integratable, but just like the last few, I see a 6 here in the u column, so I'm going to go one more time so I can get that highly coveted 0. Derivative, integral, and multiply. Great. So Now that we have all of that, let's scoot this over a little bit and let's start assembling our antiderivative. We're going to start with an addition. So diagonally, we're going to add, multiply and add. Then our next step is to subtract the next diagonal. Then we're going to add the next diagonal. And then we'll subtract the very last diagonal. And since the next line is going to be a 0, we'll add our constant now. Okay, wow, this is quite a thing to behold. So let's start multiplying things together. I think in our first addend over here, we can just kind of put that x cubed inside, and then we'll be pretty safe. In our next addend, we're going to multiply that 3x squared, and we'll just put that on the inside, I suppose. In our next addend over here, we've got a negative sign, so I'm going to go ahead and take the opportunity to change this to minus a positive. And then we'll multiply that 6x to the inside. Maybe we could take that 6 and 8, and we can reduce that. Great. And in our last addend, we can move the 6 inside the parenthesis without any penalty. And then we could reduce 6 and 16. I think we could divide everything by 2. And then I don't think we need the parentheses anymore. And that looks like we're ready to start factoring things. All right. So what do I see here? Well, maybe the first thing we should do is to group everything except for the constant. I see an e to the negative 2x on every term. So we could definitely factor that out. And then now taking a look at all of my denominators, 2, 4, 4, and 8. At least it seems like the least common multiple is going to be 8. So let's turn everything into 8s. 1/2, that's 4/8. 1/4, that's 2/8. And another 2/8. And let's see, let's get all the numerators out of there. We'll put those in front of our x's. And now everything has a 1/8, and we can definitely factor that out. And I don't like how that lead term is negative, so I think I'm going to divide out a negative also. While we're at it, let's make it a negative. Looks like a negative. No, that might be it actually. Just a negative. So that's a good look at our antiderivative. And I was just reminded now that we're actually not finished yet because this was a definite integral or a initial value problem. So we're saying that y is going to equal our antiderivative here, and when y is going to be equal to -1 whenever x equals 0. We can simplify this. And then just solve for c, which finally gives us our solution. Now that was probably one of the more difficult problems that we're going to end up doing. Let's see, we probably have time for a couple more questions. So here's another initial value problem, number 21. I'm looking at the integrand, or the perspective integrand, and I see a algebraic function and I see a trig function. So when those multiply together, that sounds like I'm going to be using the integral by parts method, with my u being x plus 2 and my dv being sine x. So let's try to speed things along by using the tabular method. I'm not 100% sure about how many rows I'm going to need, but I do know that u is going to be x plus 2 and dv is going to be sine x, and then we'll multiply like we always do. One nice little feature about using the tabular method with 3 columns is that over here, when you multiply u and dv, you should get the original integrand over here. So a little bit of error checking. All right, let's take our derivative, our integral. We'll multiply. We get something that is integratable. I know what the antiderivative of cosine is, but I also see the 1 there, so I want to go one more line just so I can get the 0. So derivative, antiderivative, multiply. And now we're ready to put together our antiderivative, starting with an addition. And now a subtraction. And I've reached the 0 row down over here. So I know I can just put a plus c now. Great. Well, let's straighten out all of the positives and negative signs. Move this negative to the front. And then we'll use these 2 negatives to make this an addition. And then on this back half over here, we have a plus 1 sine x. Well, that's just plus sine x. Okay, this is a good look now. We have a general solution. Y is equal to negative quantity x plus 2 cosine x plus sine x plus c. And now we'll use this and our initial condition to solve the initial value problem. Let's write this again. And we know y equals 2 whenever x equals 0. All right, cosine of 0 is 1. Sine of 0 is 0. You can simplify this a little bit more. 0 plus 2 is 2. Plus 0 is not really necessary. And from here, it looks like c is going to be equal to 4. So that gives us our particular solution. Well, I think we have time for at least one more. So let's see. Use separation of variables to solve the initial value problem on number 22. So let's write that down as a initial value problem. Y prime is, of course, dy dx. And I really don't like the way we have the quantity of x, y squared, because it's difficult to separate variables with that. So I'm going to re-express that as x squared, y squared. Okay, now I can multiply by dx and then divide by y squared. And that does it for the separation of variables. My next step here is to do some integration. So let's do some integration. Now with this one, it's probably easier if we look at y to the negative 2 power rather than dy over y squared. Okay, that looks nice. Let's go ahead and take antiderivatives of the left and the right. Negative 2 plus 1 is negative 1, so I'm going to get y to the negative 1 over negative 1 on the left. And on the right side, 2 plus 1 is 3, so I'm going to get x cubed over 3, and I'll put the plus constant on the right. All right, that looks pretty good. Let's multiply a -1 to both sides. My left side, of course, the negatives are just going to cancel. And on my right side, I'm going to get a -x³ / 3 minus c. But really, minus c, well, that's still a constant, so I'd rather see that as plus c. And then y to the -1 power on the left, we'll make that 1/y. Great. Now, I think the next thing that we should do is take the reciprocal of the left and the right. Now, on the left side, 1/1/y, well, that's just y. And on the right side, that's kind of difficult to do. Let's see. Let's move the denominator into a common denominator. So that c, we can make that 3c over c. But of course, 3c is just a constant, so actually I don't need 3c. I can just make it c. And now that I have a common denominator on the denominator, I can just combine them into one single fraction. And now that I have that on the denominator, all I have to do is take the reciprocal of this, and I have my result. Actually, I'm looking at this, and I don't like the way it's written. I just want to remember that this negative sign here was part of the x, so I'll move it with the x first, and then I'll take my derivative, my reciprocal. Looking good. I have this is a general solution. It's in terms of x. I've solved for y. So now I'm going to substitute to find my particular solution. So here's my general solution. And I know that when y is equal to 1, then x is also equal to 1. 1 cubed is just 1. So it looks like in order to make this happen, my c, it has to be 4. And of course, now that I know what c is, I can write my particular solution. And that does it for this problem. And I think that does it for this video. Let's see. Just a few problems this time. I think we started with number 17 and finished up at number 22. So have a good one, and we'll see you for the next video here on AP Calculus. See ya.